Okay, let's discuss about bending stresses. In this video, we're gonna talk specifically about the normal stress due to bending. The expression for that is this. And I'm pretty sure you are crazy for understand how to derive the expression thinking about a bending like this and its derivation. Okay, but first we have to remain some things. For example, if you think on an aircraft, the wings are beams. In that particular case, people called y for the longitudinal direction, but in fact, normally we call it as x. You know, and you could develop the shear force and bending moment starting with the lift distributed load. And we have to remain that if we derive the bending moment, we could obtain the shear force. And also, if we integrate the shear force, we could obtain the bending moment, isn't it? But let's think about something more simple. Let's think about a mattress like this. Okay, if you note, when we bend the mattress, the vertical lines we draw, some remains vertical while others get angled. Yeah? What it means? In fact, what it means is that the fibers at the top get shorter and the fibers at the bottom extend, getting longer. Yeah? And also, what it means is that there is some place, some surface, and some axis that remains the original length. This is called neutral axis. And here is an spoiler. The neutral axis, this neutral axis that remains the original length, is located at the centroid of the cross section of the beam. This case, when we applied a force and we have the unload, and the reaction is similar of this other system when we apply two bending moments. This is the same system, a beam loaded by bending moments. And what if we want to know about the stress at the neutral axis? Then the normal stress at the neutral axis is zero, since it remains the original length. It means that no tensile and no compression were applied. Yeah, but what if we want to know about the stress at a point P located downward at a certain distance, in fact called y distance? You know, this is the neutral axis and the point P is located at a distance y downward, isn't it? And remember, we know the shear force and the bending moment at this point. In fact, at any point, because we know the shear force and bending moment diagrams. It means that we know the shear force and bending moment at any x location along the beam. Okay, so we could continue. So remember, in that beam, you have a radius called rho until the neutral axis. You know, this is the center of that bending. An angle in radians called theta. This 3D view is the same that this side view. So let's check that. Since we remains the Hooke's law when we study the stress strain diagram, we know that stress is equal to the Young's modulus times the strain, and the strain is calculated as the change in length by original length. But what is the change in length here? You know that AB remains the original length, while CD get longer. So the change in length is the difference between CD and AB. Okay, so if we know that AB is an arc is equal to radius times the angle in radians, we know that AB is equal to rho times theta, and CD is the same, radius times angle, but the radius for CD is the same rho plus y, the same rho until the neutral axis plus y. Okay, so substituting this AB and CD expression on the strain expression, we could cancel some terms and get some simple that we also could simplify even more, and we obtain then that strain is equal to y over rho. And if we substitute this expression of strain into the Hooke's law, we get this, a new expression for stress. Okay, but let's think about another idea. We know that a normal stress is equal to a normal force by area. So the force is equal to stress times area, isn't it? If we know the stress here at the base of our section, we can get the force and at a specific point as P, yeah, as stress times area. Okay, so the force at point P is the stress at point P times area. Okay, and what about the moment? Since we are thinking about bending moment, the moment could be calculated as force times distance. If we know that force is this, which is the distance? The distance is the distance between the neutral axis and point P. Since at neutral axis the force is 0. Okay, so force times distance, and distance is y, and force could be substituted by stress times area, and organizing for the whole sectional area, we can get that moment is equal to integral of stress times y dA. But stress is this. So we substitute here, and organizing the integral, we can put out the constants, and we get the expression of integral of y squared times dA. That is the moment of inertia. Yeah, so moment is equal to modulus times E over rho. Okay, let's continue. If you check this expression for moment and this expression for stress, you could note that modulus over rho is present in both. So we take that expression from the first is equal to stress over y. Stress over y. From the second formula, we can get that is E over rho equal to moment over inertia. Yeah, and in such manner we got that stress, normal stress due to bending, is equal to moments times y over inertia, the flexural formula. Let's think about this. moment obtained by the moment diagram, shear force and bending moment diagram. Yeah, inertia, the inertia of the whole section area. Yeah, and y is the distance between neutral axis and the point we are studying. Remember, since this point is here, the y is measured since the neutral axis and the point of study. That's it. If you apply the formula for a point right in the neutral axis, you will get 0 because y is measured from the neutral axis, so that distance will be 0, isn't it? And if you apply the formula for a point at the fiber at the top of the beam or at the bottom of the beam, you will obtain the maximum normal stress since y is maximum. Yeah, and for any other in that case we call the y as c, as you can see in books, m c over I, because it's the maximum normal stress due to bending. But for any other point as P, that is not in the neutral axis but also not at the external fiber, is m times y over inertia.